Next question we may want to ask is, how do we know if there's no concavity or there are no inflection points? Well, there are a couple of intuitive ways to think about this, and a function is going to be concave up when the slopes are constantly increasing. So from perhaps going negative to less negative to less negative to eventually positive, 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 or the slopes are going from positive to less positive, and then eventually negative. But not all functions have concave up or concave down shapes. For example, if we plot a linear function, we know that the linear function is neither concave up nor concave down. The slope is, in fact, constant. Anywhere you look at the slope of the instantaneous rate of change, that slope is always identical. So we would expect there to be no concavity. So one example would be f of x equals 3x plus 6. So how mathematically do we arrive at the fact that there are no inflection points if we know nothing about the function? Again, f prime of x, we take the first derivative. The derivative of f of x is just going to be 3. In other words, the slope is constantly 3 along this function, and the derivative of that function is 0. So you could say, well, oh, Milos, I'm going to set this equal to 0, and I'm going to solve for x. Well, if you do that, you get 0 equals 0, which there's nothing to solve for. And the fact that this function has a second derivative of 0 everywhere, this means that this function is neither concave down nor concave up, which means a lot of times the function is going to be linear. Okay, so that's one way we know there's no concavity is we take the second derivative, and the second derivative is neither positive nor negative. It's a constant 0 value. How about the function x squared plus 10x plus 1? Well, from, again, what we know, this is a parabola that opens upwards, and if it opens upwards, then the function is concave down everywhere. So we've noticed this already, hopefully, with the derivatives of quadratic functions. The derivative of this quadratic is going to be 2x plus 10. And the derivative of that is going to be f double prime of x equals 2. Okay, well, first of all, the second derivative is a positive 2. That means that the function is going to be concave up everywhere. And you could again say, well, I'm going to set this equal to 0, and I'm going to solve for x. But wait a minute. There is no x to solve for. And the statement 0 equals 2 is a false statement. 0 can't be equal to 2. So already, if we try to solve mathematically, this tells us that it's impossible to solve for inflection points because guess what? There are none. The function is always concave down. And again, an inflection point is a change in concavity. So not all functions have a change in concavity. In fact, some functions don't even have concavity, like linear functions. Well, let's look at a more interesting example where we deal with application. So why would we be interested in the second derivative other than it tells us something about the function? Well, in business, the inflection point is called the point of diminishing returns. And that is essentially the point at which the returns begin increasing at a decreasing rate. So the law of diminishing returns in business says that when an input is increased, such as labor, while all others are held constant, the resulting increase in production will become larger and larger until the point of diminishing returns. After the point of diminishing returns, the increase in production becomes smaller and smaller. So notice there are a couple of things to take into account here. First of all, we're not arguing that your returns are decreasing. We're just saying that the increase in production will become larger and larger. So the increase in production becomes, first of all, positive, and then it's more positive and more positive and more positive until the point of diminishing returns. So it's not that the function starts to go down, it's just that after the point of diminishing returns, the increase in production, increase is the key word here, becomes smaller and smaller. So the increase becomes smaller and smaller and smaller and smaller. So again, we have kind of this concave up shape to this concave down shape. And that's specific. We want to go from concave up to concave down when we're dealing with law of diminishing returns. So let's say, for example, a company generates profits according to the function P of n equals 400 e to the n, where e is the constant 2.71828, minus 0.1 e to the 2n, where n represents the number of crates of beer sold. Is there a point of diminishing returns? So in other words, is there an inflection point? Well, let's do that first. Let's take the derivative, p prime of n, and we get 400 e to the n, because the derivative of e to the n is e to the n, or e to the x is e to the x, minus, now we have a chain rule here, so we have minus 0.1. What's the derivative of e to the stuff? Well, it's e to the stuff times the derivative of the stuff, because it's not just an n or just an x up here, so the derivative of 2n is 2, and so that means that p prime of n will simplify to 400 e to the n minus 0.2 e to the 2n, and the derivative of that in a much similar fashion is the derivative of this function. Well, the derivative of 400 e to the n is still 400 e to the n minus 0.2, and the derivative of e to the stuff is e to the stuff. We could do natural log of e times e to the stuff, but natural log of e is 1. And the derivative of the exponent, or of the stuff, is just 2. And so the second derivative is 400 e to the n minus 0.2 times 2. This is all multiplication here, so we can multiply in any order we want, 0.4 e to the 2n. And now we want to ask, are there any inflection points? Well, an inflection point occurs potentially when the second derivative is 0, so we set this equal to 0, and we have to solve for m. So I picked this example because, of course, there's a little bit more algebra involved. So how would we go about doing this? Well, there are a number of ways, but the two properties that we need is, number one, that the natural log of e to the b power is equal to b times the natural log of e. So this is the property we know as that the exponent of whatever the base is drops down as a multiplier. So it comes down here out front, if you want to think about it that way, b times the natural log of e, which is simply equal to b because the natural log of e is 1. The other property that we want to use is that the natural log of a product, a times b, is equal to the natural log of a plus the natural log of b. And we can prove that. We won't do that here. So we need to use those two properties here in order to isolate n. To make this a little more manageable, we could either move one component to the other or divide through by a constant. So if we divide through by 0.4, we divide both sides by 0.4. That will at least eliminate one of the exponents. And so 400 divided by 0.4 is going to be 1,000 times e to the n minus e to the 2n. And so now what I'll do is I will go ahead and move the negative e to 2n to the other side, because for one, if I take the natural log of both sides now, we end up with extra constants that we don't need. So I'll go ahead and do this. And now if I take the natural log of both sides, remember, as long as I do the same thing to both sides, the same operation, I can perfectly legally do that. I get the natural log of 1,000 plus the natural log of e to the n. Right? By this property here, the right-hand side can be written that way. Now, we also know that the natural log of e to a power is the power times the natural log of e. In other words, really what happens is the natural log of e to the 2n cancels out. But let me go ahead and write it out fully. So this is 2n times the natural log of e equals, I'm going to leave this because this is a constant, so natural log of 1,000 plus the natural log of e to the n. So again, I get to use property 1 here and move that exponent as a coefficient times the natural log of e. So that gives me 2n equals the natural log of 1,000 plus n, and now I need to solve for n, so this becomes, again, the natural log of 1,000 is a constant, so I can go ahead and isolate n, and if I subtract n from both sides, then I get, I'm going to write it up here, 1n equals the natural log of 1,000. Well, what's the natural log of 1,000? The natural log of 1,000 is something I can compute in my calculator, and I get approximately 6.91. So this is a potential inflection point. How do I know it's an inflection point? Well, again, what I have to do is to make sure that at x, or in this case, n equals 6.91, that I change concavity at that point, that either I go from concave up to concave down, or concave down to concave up. Now, if this is a point of diminishing returns, that naturally means that I go from concave up to concave down. And so what I'm hoping for is that that is the case. Well, if I test, again, the second derivative, which is this guy here, at a point that is to the left of n equals 6.91, for example, if I test p prime of 0, what I will end up with is 400 e to the 0 minus 0.4 e to the 0, which is 400 minus 0.4, which is a positive number. And here, if I test something like p double prime of 7, I'm going to get a negative number. And you can verify, please actually do verify that that's the case. And now we can take a look at the graph to confirm that. So I've begun graphing the function here, and I'm going to change my y-axis. And all I'm going to do is just keep adding a 1 here until I finally see that maximum. There it is. Okay, so now I can see that I have a maximum, first of all, right there. So that's my maximum possible profit. And if I plot the second derivative, which we know now is 400 e to the x, I'm not going to even plot the first derivative, but if I do that, then what I should notice, e to the 2x, is that where that derivative crosses the horizontal axis, that's my critical point. That's actually an absolute maximum at 7.601. But I don't want that function. What I really want to plot is the second derivative, 400 e to the x minus 0.4 e to the 2x. And what I see is that this second derivative is equal to 0, guess what? When x is equal to 6.91, or approximately 6.91, which is exactly what we came up with here. At n equals 6.91, I have a critical point, and that is the point at which, right around here, that corresponds to that output, where the function officially goes from concave up to concave down. So when I'm selling 6.91, whatever, million, thousand, hundreds of crates of beer, that's where my production or my revenue is still rising, but it's rising at an ever so decreasing rate. So is the point of inflection the number of crates you should manufacture? Not necessarily. That's just saying that's the point at which your growth in revenue becomes smaller and smaller. We'll take a look at this application briefly, but you may be wondering, well, where else does this apply? An example in medicine, it has to do with what's called a drug response curve. And I challenge you to try this out. We're not going to do it here, but the drug response curve describes the level of medication in the bloodstream after a drug is administered. A surge function, S of t equals a times t to the p e to the negative kt, where best guess what, a, p, and k are just some constants, and those are specific to the drug you're using, is often used to model the response curve, reflecting an initial surge in the drug level and then a more gradual decline. So basically what's happening over time here is that you get a big surge in the amount of drug in the bloodstream, and then the amount of the rate at which that amount of drug is increasing begins to slowly, it's still increasing in the bloodstream, but the rate at which that's happening tends to decrease. And there's an inflection point somewhere around here. And a lot of times in medicine, that inflection point is something used to describe the sensitivity of the drug for that particular person. So if that rate of change at the inflection point or just before that is too high, that the amount in the bloodstream is growing at a very rapid rate right there, you may notice that that person is very sensitive to that drug. And in this case, if we go ahead and plot this, we can see where that point takes place roughly. So for these values a, p, and k given in this problem, first of all, the first derivative requires me to use a product rule because I have a product of 0.01x to the 4, a power function, and e to the negative 0.07x, an exponential function. So if I use the power rule, I can graph the first derivative, and what I should notice is that the first derivative corresponds to a maximum at the point 57.5 143, and then that is the dosage inside the bloodstream. And then I can see that I have a